Okay, so we've just looked at those functions. We were the introduction to the functions. Now we're going to think about their inverse functions, okay? Their inverse functions have some interesting things to talk about. Just a note on how you say the inverse functions. With trigonometry, if you were saying the inverse of sine, you know that we write that as arc sine x. Whereas if it's the inverse sine function, we don't write arc sine, but just we, for some reason, don't put the c to try and make it feel a bit different. So it would be r sine x. You would then also have r tan x and r cos x, rather than arc cos x. So they don't have a c in them when you do it with the hyperbolic trig functions, okay? They don't have a c with them. Now I have sketched here in red cos x and sine x. And I've reflected them in the line y equals x to come up with y equals r sine x and y equals r cos x. It could be, but so cos x could look like this. It could also look like this. It just depends on what the axes really look like. And I guess if you think about it with a heavy chain, if you held a chain at this point here, it would go like that and still have that kind of flat sort of bottom to it, okay? So why, though, have I suddenly decided to start drawing cos x in a different way? Yeah, why have I only drawn the positive values only for cos x? When I'm talking about finding the inverse function. Pardon? It does have an inverse. This is the inverse here. Think about what I've taught you in chapter 2 of pure year 2, functions, and when functions... Yeah, it's about making a function, when you have its inverse, it can't be a one-to-many function, which is what cosh is, because when you do the inverse of one-to-many, you get many to one, and many to one is not a function, so the inverse function wouldn't exist. So that's why we're only taking this branch of it, because if I had the whole branch, I would reflect it and get this, and r cos x is then no longer a function, because I have one thing going to many solutions. So we restrict the domain of cos x in order for us to be able to think about what the graph should look like for r cos x, okay? Don't know why I've decided to draw tan down here. I'm going to then try and draw the reflection of tan. This is, I find, quite difficult. So it's, instead of the asymptotes being at 1 and minus 1 on the y-axis, they're going to be on the x-axis instead. And so if it was reflecting along here, it's going to go like this and this. I think that's right. Is that right? Yeah. That's been reflected in the line y equals x. So this is y equals r tan x. You don't really need to know these graphs. Well, you do need to know them. They're interesting, but they're never going to ask you to sketch them because you could literally type them into your graphics calculator. But it's just thinking about how the properties of these are like all strung together, okay? So that's what the inverse hyperbolic functions look like on graphs. But we are interested to see what these inverse hyperbolic functions are as definitions. Because at the beginning, we gave you the definitions of what sine, cos, and tan are in terms of the exponential function. So it should make sense that we can have definitions of the inverse functions of sine, cos, and tan. And even more than that, because the hyperbolic functions can be written in terms of e, the inverse hyperbolic functions should be able to be expressed in terms of ln. Because if L and E are related to each other by inverses, if sine, cosine, and tan are written in terms of E, then r sine, r cos, and r tan should all be able to be written in terms of ln. So I'm going to do all three of these proofs. I might do two and then you try the third one. But I'm going to try and prove that r sine x is ln of x plus the square root of x squared plus 1. And you will be using this. This one does come up in the formula book, though. And this for me, is when my memory reaches its limit. I can't memorize this, but it is in the formula book, and you will be using this one. Okay, so I'm going to start off, and you can do inverses in lots of ways. You might see it different in a mark scheme, but I'm going to do it in this way because it just is going to link into the way we've done inverse functions from chapter 2 of pure. So I'm going to let f of x equal sin x, which means that the inverse function will be r sin x. Okay? So if y is equal to sin x, what process did we go through in normal maths A level to do inverses, to find inverse functions? Say that again. Switch x and y, and then make y the subject. So I'm going to switch x and y, and then I'm going to rearrange to make y the subject, which will then become r sin x. So I get that x equals sin y. What do you think I should do now? Because all that's really going to happen is I might say, okay, well, great, y equals r sin x. Therefore, f of x is inverse is equal to r sin x. But that's not what I'm trying to show. I'm trying to show that it's this. Yes, exactly. I'm going to say that x is equal to a half of sin y. Sorry, a half e to the y minus e to the minus y. That is what sin y is. And we're now going to try and make y the subject of this equation that I've got here. So, double both sides. 2x equals e to the y minus e to the minus y. What technique did we come across before that will help us to do this? The quadratic technique. We're going to use the quadratic technique, and we're going to multiply everything by e to the y. So we get 2x e to the y equals e to the 2y minus 1. And this is a quadratic equation, so I will set everything to one side. And then we need to solve this quadratic equation. How shall I solve this quadratic equation? Can I factorize? I could, I'll give you two options. We can either complete the square or use the formula. Should we complete the square? Okay, let's complete the square. I don't really like the formula. So if I complete the square, what would be the brackets that we have here? Say that again. What would be the bit inside the brackets? I'm confused. It would, oh, minus x, e to the power. I didn't hear you say e to the power of y. I thought you were saying that x was in the power. So it would be e to the power of y minus x. So we've square rooted that bit, and we've halved this one. And what do we have to subtract from that? We have to subtract the x squared from completing the square, and you get the minus x squared minus 1. Then I'm going to add onto the other side the x squared plus 1. So that equals e to the y minus x all squared. I think the textbook does it using the quadratic formula, and this is way nicer. As long as you know how to complete the square, this is better. So square root both sides. It could be plus or minus, but we'll come back to that in a second. That's e to the y minus x. So I'm going to add x to this side. So that's x plus or minus the square root of x squared plus 1 equals e to the y, which means that y is ln of x plus or minus the square root of x squared plus 1. But we haven't finished, because we have a plus or minus, and they don't have a plus or minus. And then we need to try and reason, why am I not allowed to have the minus here? Very, very good. The root of x squared plus 1 is obviously going to be bigger than x, because it's 1 bigger than x squared. So if I did x minus something that was bigger than x, you would have a negative number, and you can't input negative numbers into ln. So that is why, so because root x squared plus 1 is greater than x, ln, well, we should say x minus the square root of x squared plus 1 is less than 0. So we cannot have ln of x minus the square root of x squared plus 1, because you can't put negative values into the ln. So if I just kind of finish up, Therefore, the inverse function x, which is r shine x, is ln of x plus the square root of x squared plus 1. It looked like a difficult question, and it was. You saying it was a difficult question, or it's okay? Yeah, it looks. Yeah, you're right. It looks messy, but actually, all it was completing the square and some stuff to do with logarithms. The more maths you do, the more you realise that maths is all the same as everything you've done before. It's weird. For a long time, it feels like you're learning loads of new things, and then suddenly you get to a point, and you're just like, oh, it is literally all the same thing. Takes a while though. It's probably not there yet. So I'm going to put the next one up on the board, which is for Kosh, okay? And I want you to do the one for Kosh yourself, but we're going to talk a little bit about the domain, and we're going to talk a little bit about why it's only the plus rather than the plus or minus bit, because it's slightly different for the Kosh x, okay? So I will put this bit up here, because it's the same one. No, it's not the same, sorry, I mean, it's not the same reasoning of why it's plus instead of plus or minus. There's a different reasoning why it's plus instead of plus or minus. But I want you to have a go at starting to do this one yourself. You should use the one that you've done previously to give you a bit of a guide of like how to do that proof, okay? I'm going to start doing it on the board slowly as well. So if you get stuck, you can look up. I'm just going to shut one of them. Is that okay? I know we need to keep the ventilation up, but with the door open for a bit, it's cold and noisy. If you've finished to the point that I've got to, try and think about why we don't include the negative square root.
Would you say, so you know how, like the one-to-one functions, you can't have two values, and then you limit it to x squared and 1, and then the positive value.
Yeah, but why? It's not clear to me. If you're just talking about the thing that's inside the bracket here, both of them could be positive values, couldn't they? Because this is x squared minus 1. X squared minus 1 square rooted is not bigger than x, is it? It's actually smaller than x. So when I subtract them, I'm still going to have a positive number. So why am I ignoring that one? Because I still technically have got a positive number there. It's hard, the reason why. Pardon? So there's going to be a reason, and we can talk about now why the reason the minus 1 won't work. So the reason the minus 1 won't work is because when we were talking about the functions of the graphs earlier, we want the output for y to be positive, because do you remember we said we had to ignore all of this part down here because we restricted the domain of the original one. So we don't want any output values to be negative. Now, this is because we don't really know how the ln function behaves as like brains in some kind of ways. But if the ln function overall gives you a negative, then we don't want it. And when you do ln of x minus the square root of x squared minus 1, this thing is always less than 0. Because this thing inside here is always going to be, oh my gosh, what would it be? Because if anything is smaller than e, then the power would have to be smaller than that. Pardon? No, it would be less than 0, because we're not talking about the domain, we're talking about the range of things that we've got here. And there's a proof of this, which I was going to show you about why this thing here, why the ln of this thing is less than 0. So it's because, I mean, it gives you some quite confusing things to talk through. So there's a difference of 2 squares at the beginning bit. No, it's not a difference of 2 squares. It's saying, yeah, this thing must be equal to 1. Therefore, the thing we're talking about is 1 divided by this thing. If you take ln of both sides, you get the ln of this is equal to the negative ln of this. So if this one here we know is going to be a positive answer, then the other one has to be a negative answer because of the way that it's been rearranged. And if the overall thing is a negative answer, it's giving us something that's down here on the graph, which means that we can't include it. Okay? If that doesn't make an awful lot of sense to you, I'm not surprised. It's like it took me a lot of thinking around it, and actually even now I'm kind of looking at it and I'm like, I don't think I'd ever be able to come up with that. But all I'm saying is the answer for this question is that r cosh x is only equal to this bit that we've got of it here. However, you have to be careful. If you use r cosh x to solve the equation, so you're not using r cosh x as a function, we know that there will be 2 solutions to something. If I had that cosh x was equal to 5, and I said therefore that x was r cosh of 5, there would be 2 solutions, in which case you actually can use the plus or minus, because there's a slight difference between saying what the function is versus how you might be able to use this thing. Because if I were to use this, when you think about the graph cosh x being equal to 5, there are actually going to be 2 solutions to this. There's going to be the same one of them and the negative one with it as well. So I don't know if that's going to come from, let me just quickly see if that works. So if we've got 5 plus root 24, 2.29. Yeah, so when you actually use it to solve this kind of thing, the plus or minus actually will give you the other solution. It will give you the same thing but negative. The reason we don't use it down here is because we're talking about a function, and we don't want a function to give you 2 solutions. But if we're not using it as a function, then we don't care whether it's a function or not. We just want to use it to find the solutions to things. Does that make sense or not really at all? Kind of. So there'll be some equation. When we're using it to solve equations, we will use the plus and minus. When we're not using it to solve equations, when we're doing formal maths about saying this is a function and we want to see how the function behaves, we have to be slightly stricter about how we're setting it up. So there is one more that I would like you guys to try and prove. So this time we're going to try and prove that r than x is a half ln 1 plus x over 1 minus x. And x is only allowed to be less than 1 in this case. And that's to do with what we just talked about. It's to do with this, that we know that the input values of x are between 1 and minus 1. So that's why it's like that. I'm going to do this one on the board as well. So these proof questions, if you're still going, that's fine. They are not just me showing you things, how they work, to be like, hey, this is a proof, this is kind of cool. This is something that's quite popular to examine you on, okay? It's something really popular to put in the exam. They like a proof question on this kind of thing, okay? So in the exercise, you're going to be asked to do things like this. You're going to be asked to, I don't know, to express something like r shine root 3 as natural logarithms. So all you would do, you know that r shine root 3 would be ln of, well, r shine is ln of x plus the square root of x squared plus 1. So it's going to be the ln of root 3 plus the square root of root 3 squared, which is 3 plus 1. So you just get ln of root 3 plus root 4, which is 2, ln of 2 plus root 3. And your calculators should give you that, but you're going to need to know how to do these things for future things. So at the moment, like this first lesson has very much been like here's what these functions are, here's a few things we can do with them. I'm not telling you anything that's useful about them, actually about how we use them yet. You're just going to have to trust me and see what kind of things we can do with them later. So that's what there's going to be in some of this exercise. It's a very, very short exercise. And this is a summary page, really, so that you've got everything like all in one place about what we've just done. So I've got the three functions. This is what you get in the formula book. And then I've just got all of the different hyperbolic functions and the inverse hyperbolic functions with a small sketch and with their domains sort of there for you as well. Okay? So let's have a go at doing some of exercise 6B. There's a couple of sketching questions at the beginning, so you can have a go at those if you want to. I'm more than happy for you to have a go at some of those weird kind of sketching questions. And then it's just going to be question 4, 5, 6, and 7. I'm just going to do those and finish up the homework, but it's a very, very short homework. Okay?